Ladies and gentlemen, imagine driving through one of the busiest, most unpredictable cities on Earth where every lane change could be a split-second decision between safety and chaos. Now imagine a car that doesn't just respond. It anticipates, calculates, and protects you before you even see the danger. Welcome to the future of driving where human judgment meets machine precision in real time. In the next few minutes, you're about to see how the Tesla Model Y's autopilot is redefining safety, stress, and efficiency on streets where most drivers are tested to their limits. Stay with me because this isn't just technology. It's a revolution on wheels, and a city defined by motion intensity and unpredictability. Every vehicle is tested in real time. Los Angeles is not just another market. It is a living laboratory of dense traffic, aggressive lane changes, complex intersections, sudden braking, cyclists weaving through congestion, and freeways that shift from standstill to high speed in seconds. When some drivers say they hate autopilot on the Model Y, what they are really describing is the friction between advanced automation and one of the most demanding driving environments in the world. An autopilot in the Tesla Model Y is engineered to enhance safety and reduce driver workload. It combines multiple high-resolution cameras, neural network processing, and real-time data analysis to maintain lane position, adjust speed based on surrounding traffic, and respond to vehicles and obstacles ahead. On highways, it can provide smooth lane centering and adaptive cruise control. In slower traffic, it reduces the fatigue that comes from constant acceleration and braking. In theory, it is perfectly suited for the long freeway commutes that define life in Los Angeles. But Los Angeles driving culture is not theoretical. It is assertive. It is fast. It is unpredictable. Many drivers expect split-second reactions and human-like anticipation. Autopilot by design prioritizes caution. It leaves safer following distances. It slows down when merging situations become ambiguous. It may brake more conservatively when traffic ahead behaves erratically. For drivers accustomed to aggressive merging on the 405 or tight gaps on the 101, this conservative behavior can feel hesitant. What is engineered as safety can be perceived as hesitation. And there is also a psychological shift that occurs when automation enters the equation. Drivers who have spent years mastering the flow of Los Angeles traffic may feel a loss of control when a system takes over steering and speed. Even though hands remain on the wheel and supervision is required, the sensation of shared control can feel unfamiliar. In a city where confidence behind the wheel is part of survival, that unfamiliarity can translate into frustration. An autopilot is not marketed as a replacement for attentive driving. It is a driver assistance system designed to support, not substitute. It continuously monitors lane markings surrounding vehicles and traffic patterns, but it requires human oversight. In complex urban environments, drivers must be ready to intervene. Some complaints stem from misunderstanding this boundary. When expectations exceed the system's intended capabilities, disappointment follows. The Model Y does not promise autonomous city navigation without supervision in standard autopilot mode. It promises enhanced safety and convenience within clearly defined parameters. And another factor is perception amplified by social media and local culture. Los Angeles is home to trendsetters and early adopters. When a few voices publicly criticize a feature, narratives spread quickly. A single uncomfortable braking event or unexpected disengagement can be shared widely. Yet millions of miles are driven daily with autopilot engaged, and aggregated safety data consistently shows reduced accident rates when the system is used appropriately compared to human-only driving. Individual experience is powerful, but large-scale data provides a broader context. And it is also important to recognize that autopilot improves over time. The Model Y is built on a software-centric architecture. Updates are delivered over the air, refining neural networks, enhancing object detection, improving lane interpretation, and optimizing traffic response. The vehicle you drive today is not static. It evolves. Situations that once felt abrupt or overly cautious are continuously analyzed and tuned. In a dynamic environment like Los Angeles, that iterative improvement is essential. And for some drivers, the discomfort is temporary. After weeks of use, they adapt to the system's rhythm and learn when to engage it and when to take full manual control. They begin to appreciate the reduction in stress during gridlock, the precise lane centering at night, and the consistent following distance in unpredictable traffic waves. For others, the preference remains manual driving in dense urban conditions, while reserving autopilot for open highways. And the conversation around LA drivers hating autopilot reflects something larger. It reflects the tension between human instinct and machine precision. Human drivers often rely on intuition and risk tolerance shaped by experience. Autopilot relies on data probability and safety margins. In the most demanding traffic ecosystem in the United States, that contrast becomes highly visible. And the Model Y was engineered to deliver performance efficiency and intelligent assistance in one platform. Autopilot is part of that vision, not as a shortcut, but as a step toward a safer driving future. In cities like Los Angeles, where the road tests every assumption, the technology continues to learn, adapt, and refine its understanding of the world around it, mile after mile, update after update, shaping a driving experience that blends human awareness with machine intelligence in one of the most challenging environments on Earth, and shaping a driving experience that blends human awareness with machine intelligence in one of the most challenging environments on Earth. And what often goes unrecognized in the conversation is how dramatically different Los Angeles is from the controlled environments in which many legacy driver assistance systems were first evaluated. The multi-layered interchanges, faded lane markings under harsh sunlight, sudden construction reroutes, and dense clusters of vehicles create edge cases at scale. Autopilot is designed to interpret visual data through advanced neural networks trained on billions of real-world miles. In a city where edge cases happen every few seconds, the system is constantly analyzing, predicting, and recalibrating. Every merge, every cut-in, every abrupt stop becomes data that strengthens future performance. And some drivers interpret the steering corrections or subtle braking inputs as overreactions. In reality, those micro-adjustments are deliberate safety buffers. Human drivers often operate with minimal margins, trusting reflexes and experience. Autopilot operates with statistical modeling and risk mitigation. It assumes that a vehicle drifting slightly within its lane could continue drifting. It anticipates that a car signaling late may change lanes aggressively. It prepares for the possibility that traffic ahead may decelerate faster than expected. In high-density traffic ecosystems like Los Angeles, that predictive posture can feel cautious compared to the assertiveness of local driving culture. And the Model Y integrates hardware and software as a unified system. High-resolution cameras provide 360-degree visibility. Onboard processing interprets depth, motion, and trajectory in real time. The result is a continuously updated perception model of the surrounding environment. When drivers experience phantom braking or unexpected slowdowns, those moments are investigated through telemetry and fleet-wide analysis. Improvements are deployed not through dealership visits, but through software updates that refine how the system interprets shadows, overhead signs, large trucks, or unusual road geometry. And it is also important to understand that autopilot is calibrated for broad safety standards across diverse global conditions. What feels overly conservative in Los Angeles may be precisely calibrated for complex traffic in other major cities. A system engineered for scalability must maintain consistent safety thresholds. It cannot adapt to regional aggressiveness by reducing margins. Instead, it focuses on universal principles. Maintain lane integrity, preserve following distance, respond to sudden deceleration, and require driver engagement at all times. And driver engagement remains central. The system monitors torque input on the steering wheel and prompts for attention if needed. This design reinforces shared responsibility. In a city known for distractions from smartphones to roadside billboards, this layer of accountability supports safer outcomes. When frustration arises, it is often tied to the expectation that automation should fully replicate human anticipation. Yet the purpose of autopilot is not to mirror risk-taking behavior. It is to reduce collisions, lower fatigue, and enhance situational awareness. And there is also an evolution in driving habits that accompanies advanced assistance systems. Drivers who initially resist the smoother acceleration curves and larger following gaps often discover secondary benefits. Energy efficiency improves with consistent speed modulation. Cabin comfort increases when abrupt braking decreases. Commutes that once felt exhausting become more manageable. In Los Angeles, where daily drive times frequently exceed an hour, incremental reductions in stress compound over months and years. And public perception sometimes overlooks measurable outcomes. Data collected across the fleet consistently indicates fewer accidents per mile when autopilot is engaged compared to purely manual driving. While individual experiences vary, large-scale analytics reveal patterns that isolated anecdotes cannot. Each mile driven contributes to a continuously improving neural network. Each disengagement is a learning opportunity. Each complex interchange navigated under supervision refines the collective intelligence of the system. And the Model Y represents a software-defined approach to mobility. Hardware provides the sensing foundation, but intelligence evolves digitally. This means that a driver who activates autopilot today benefits from insights gathered across millions of vehicles operating in environments just as demanding as Los Angeles. The city becomes both a challenge and a catalyst. Its density accelerates learning cycles. Its unpredictability sharpens perception models. Its constant motion stress tests every update deployed. And for drivers who prefer full manual control in urban cores, the flexibility remains. Autopilot can be disengaged instantly. Performance steering precision and regenerative braking remain fully accessible. The vehicle does not impose automation. It offers it. The relationship between driver and system is dynamic, adaptable to personal comfort levels and specific road conditions. And as traffic density increases globally and urban infrastructures grow more complex, advanced driver assistance will play a larger role in reducing collision rates and easing congestion-related stress. Los Angeles stands at the forefront of that transformation. The feedback, criticism, and real-world usage from its drivers feed directly into continuous refinement. What begins as skepticism often transitions into calibrated trust as updates improve predictability and smoothness. And in the broader context, the debate around autopilot in the Model Y is not a rejection of innovation. It is a natural phase in the adoption curve of transformative technology. Expectations are high because the potential is high. In one of the most demanding driving environments in the world, the system continues to process, adapt, and learn from every lane change, every merge, every sudden stop, integrating human supervision with machine precision in a way that redefines how assistance technology functions under pressure, and integrating human supervision with machine precision in a way that redefines how assistance technology functions under pressure. And pressure is the defining variable in Los Angeles traffic. Vehicles occupy every available gap. Motorcycles filter between lanes. Delivery vans pause unpredictably. Sun glare reflects off glass towers and chrome surfaces, altering contrast and visibility in fractions of a second. In this environment, autopilot is not reacting to a single stimulus. It is simultaneously tracking dozens of moving objects, predicting trajectories, and calculating safe paths forward in real time. The computational workload behind what feels like a simple lane-centering experience is immense. And when drivers report discomfort, it is often because the system behaves differently than instinct. A human driver may accelerate assertively to prevent another vehicle from merging ahead. Autopilot may ease off the accelerator, allowing the merge to happen smoothly. A human driver may hold speed through a narrowing lane, relying on confidence and spatial judgment. Autopilot may subtly reduce speed to maintain optimal lateral distance. These decisions are rooted in safety modeling, not competitiveness. In a culture where defensive and offensive driving blend together, this distinction becomes noticeable. And there is also the factor of expectation shaped by language. The term autopilot can evoke aviation-level autonomy in the minds of some users. In practice, the system is designed for active supervision. It supports steering, acceleration, and braking under specific conditions, but it does not replace driver awareness. The Model Y communicates this through visual cues on the display, audible alerts, and steering prompts. Engagement is a continuous dialogue between driver and system. When that dialogue is misunderstood, frustration can emerge. And yet the technological foundation remains transformative. Vision-based neural networks interpret road geometry without reliance on traditional sensor stacks. The system learns from rare events, unexpected debris, unconventional vehicle shapes, unusual lane markings, and integrates those insights into future builds. Los Angeles, with its constant roadwork and evolving infrastructure, becomes a high-frequency data source that accelerates refinement cycles. What is perceived as a flaw in one moment becomes training input that strengthens performance across the fleet. And drivers who commit to understanding the system's behavior patterns often discover predictability within the caution. Following distances are consistent. Lane centering is deliberate. Acceleration curves are smooth and energy efficient. In extended freeway congestion where stop-and-go waves ripple endlessly, autopilot maintains composure without fatigue. Human reaction times degrade over long commutes. Software reaction times remain constant. This stability contributes to reduced stress accumulation, even when traffic density remains high. And another dimension of the conversation involves trust calibration. Trust in automation is built gradually. Initial over-reliance can lead to disappointment if the system requests intervention. Under-reliance can prevent drivers from experiencing its full benefits. Optimal use lies in understanding when highway conditions are structured enough for smooth engagement, and when dense urban streets require more frequent oversight. The Model Y empowers that choice seamlessly, allowing immediate disengagement through steering input or braking. And as software-defined vehicles become more prevalent, user feedback loops grow tighter. Telemetry, collected with privacy safeguards, identifies patterns behind abrupt braking reports or disengagement clusters. Engineers analyze contextual data, lighting conditions, vehicle speed, surrounding traffic behavior, and map geometry. Adjustments are validated through simulation and fleet shadow testing before broader deployment. This iterative architecture ensures that the driving experience evolves continuously rather than remaining fixed at the point of purchase. And in cities like Los Angeles, the emotional dimension of driving cannot be ignored. Commutes are intertwined with work schedules, family responsibilities, and daily stress. Any perceived unpredictability in vehicle behavior can amplify tension. For that reason, refinement prioritizes smoothness and transparency. Display visualizations show detected vehicles' lane boundaries and intended paths, offering insight into what the system sees. This visual feedback builds comprehension and gradually aligns driver expectation with system logic. And energy management also plays a role. Smooth deceleration and optimized following distance contribute to regenerative braking efficiency. Over time, this translates to measurable range preservation. In a city with long commuting distances, maximizing efficiency without sacrificing safety is integral to the ownership experience. Autopilot's driving style supports that objective by minimizing abrupt throttle changes and unnecessary speed fluctuations. And the broader transportation landscape is shifting toward increased automation, not as a novelty, but as a safety imperative. Human error remains the leading cause of collisions worldwide. Assistance systems are engineered to reduce that variable. In environments where complexity peaks, multi-lane interchanges, sudden bottlenecks, erratic merges, the partnership between attentive drivers and machine intelligence creates redundancy. Redundancy reduces risk. And what begins as resistance in a high-intensity market often becomes adaptation, as updates refine edge case handling and drivers recalibrate expectations. The Model Y does not claim perfection in every scenario. It embodies progress, software-driven, data-informed, and continuously improving. In the dense arteries of Los Angeles, where every mile tests precision and patience, the interaction between driver and autopilot becomes part of a larger evolution in mobility where safety margins, computational awareness, and human judgment converge under constant real-world pressure, and where safety margins, computational awareness, and human judgment converge under constant real-world pressure. And in addition to the immediate benefits of safety and driver assistance, the Model Y's autopilot introduces a paradigm shift in how daily commutes are experienced. Los Angeles is a city where the unexpected is routine. A lane may close without warning, a pedestrian may appear between vehicles, or a cyclist may change direction mid-intersection. Traditional driving relies on reaction time and experience to navigate these scenarios, but autopilot adds a predictive layer. It evaluates potential outcomes based on movement patterns, historical data, and probabilistic modeling. This predictive capability allows the vehicle to anticipate situations before they fully unfold, often smoothing interactions that could otherwise escalate into abrupt braking or evasive maneuvers. And the system's capacity to handle multi-vehicle dynamics is particularly relevant in heavy traffic corridors like the 405 or the 10 freeway. Here, vehicles merge, weave, and brake in ways that human drivers unconsciously anticipate. Autopilot, however, calculates safe responses algorithmically. It maintains consistent lane positioning and safe following distances, reducing the likelihood of chain reaction incidents. While some drivers may initially perceive this as overly cautious, it is a deliberate trade-off. A momentary deceleration or hesitation translates into measurable reductions in collision risk. Over thousands of miles, these incremental adjustments create a safety buffer that human reflexes alone cannot consistently replicate. And the interaction between driver and system also evolves over time. Initial experiences with autopilot in congested urban areas can feel rigid, because the system adheres strictly to safety parameters. However, as drivers engage repeatedly with the vehicle, they learn the system's decision-making logic. They come to recognize the subtle cues, speed modulation, lane centering behavior, and spacing adjustments that indicate when autopilot is actively evaluating traffic versus executing a standard maneuver. This familiarity fosters trust and confidence, allowing drivers to leverage the technology more effectively while maintaining ultimate control. And autopilot's adaptability extends to complex environmental conditions as well. Los Angeles presents unique challenges such as glare from low-angle sunlight, reflective surfaces on high-rise buildings, and sudden microclimates caused by ocean breezes. The vehicle's camera suite combined with neural network processing detects these variations and adjusts its perception algorithms in real time. Lane markings, vehicle contours, and obstacles are evaluated dynamically, allowing autopilot to maintain safe operation, even when human visual perception may be compromised. Over time, software updates further enhance this adaptability, incorporating new patterns and improving accuracy across diverse conditions. And the fleet learning approach amplifies the system's capability. Every mile driven by every Model Y contributes to a vast database of real-world scenarios. Edge cases encountered in Los Angeles. Aggressive lane merges, unusual signage, temporary construction patterns inform system improvements for all vehicles. When drivers in one part of the city experience sudden braking or complex merging behavior, the insights from those events help refine algorithms and calibrations. The vehicle evolves not as a static product, but as a living system continuously learning from a collective experience that spans millions of miles globally. And efficiency is another critical factor. Autopilot's smooth speed modulation and anticipation of traffic flows reduce energy consumption through optimized regenerative braking and reduced acceleration peaks. In stop-and-go traffic that dominates Los Angeles commutes, these incremental improvements translate into meaningful gains in range and battery longevity. A driver using autopilot experiences not only safety benefits, but also improved operational efficiency, reinforcing the holistic value of the system beyond simple automation. And psychologically, the system reshapes the perception of urban driving. Long commutes historically associated with stress, fatigue, and constant vigilance become more manageable. By automating repetitive and cognitively demanding tasks, the vehicle allows drivers to allocate attention more strategically, monitoring intersections, anticipating erratic behavior, or preparing for complex navigation sequences, while reducing mental strain. This reallocation of cognitive resources can transform daily driving from a high-stress chore into a more measured and controlled experience. An autopilot also strengthens situational awareness. Visualizations on the touchscreen display provide real-time information about surrounding vehicles, lane boundaries, and potential hazards. This transparency allows drivers to see what the vehicle perceives and how it intends to respond. For drivers adapting to automation, this visual feedback is invaluable. It bridges the gap between human intuition and algorithmic decision-making, making the system's behavior predictable and understandable. When a vehicle slows unexpectedly or adjusts lane positioning, the driver can immediately contextualize the action and respond appropriately if necessary. And the system's contribution to urban safety extends beyond individual vehicle performance. In aggregate, autopilot reduces erratic braking, unsafe following distances, and collision propagation, contributing to smoother traffic flow. In a city plagued by congestion, even small improvements in acceleration and deceleration patterns across thousands of vehicles can reduce traffic waves and improve overall efficiency. These systemic effects highlight the broader societal benefits of autonomous assist technologies in dense metropolitan areas. An integration with navigation and map data further enhances the Model Y's capabilities. The vehicle anticipates exits, lane splits, and intersections well in advance, using predictive pathing to position itself optimally. This coordination reduces last-minute lane changes, which are a common source of accidents in multi-lane urban freeways. When autopilot is active, it combines sensor inputs, predictive modeling, and map awareness to execute maneuvers that are smooth, safe, and reliable, even under the most challenging traffic conditions. And Los Angeles, with its constant pressure, unpredictable patterns, and high driver expectations, exemplifies the environment in which autopilot demonstrates both its potential and its value. Each interaction, whether smooth or initially frustrating, is part of a continuous feedback loop. Human drivers adapt, the system evolves, and the partnership between human judgment and machine intelligence strengthens. In this dynamic, challenging urban ecosystem, the Model Y exemplifies a new standard of driver assistance where safety, efficiency, and cognitive support converge to redefine the daily commute, mile after mile, moment after moment, under conditions that test the limits of both human and machine alike.